Dear colleagues, my colleague Elisabeth Dagrada, book conservator at the Sorbonne Interuniversity Library, and I, Laury Grard, also book conservator at the same institution, had the light to present the result of our research about conservation bindings for Western medieval manuscripts on parchment text blocks. We are particularly grateful to the IADA board for allowing us to share our study. The R-CODEX project began 3 years ago as a result of an observation shared by the team of the Conservation Studio at the Sorbonne Interuniversity Library and the Conservation Studio of the Montpellier Interuniversity Documentary Cooperation Service. Conservation bindings are a last resort solution for the text blocks lacking bindings or whose existing ones are inadequate or harmful for the preservation. So it's not a treatment commonly carried out. But when it's needed, their creation poses ethical and technical challenges for book conservators worldwide. Existing models, for example Clarkson and Espinosa models, could fail to address the diverse cases met in practice. Additionally, the lack of mechanical studies limit conservators' ability to ensure that their technical choices provide optimal long-term preservation. The R-CODEX project, combining theoretical analysis with mechanical testing, aimed to re-examine traditional medieval bookbinding practices in order to deepen our understanding of their mechanical performance. Given the extensive scope of the study, the initial phase of the project is devoted exclusively to an in-depth examination of the sewing. Following this key issue, what mechanical phenomena occur during spine opening? Which materials provide a strong and well-suited sewing for the text block? Which sewing techniques and materials could minimize weak points on the spine? The R-CODEX project aims to develop a decision support tool for book conservators. The project methodology began with a comprehensive literature review, resulting in a state-of-the-art of sewing materials and techniques. Then, it's complemented by a survey designed to uncover knowledge and practices that have not been formally published. Based on these gaps identified in the literature, a protocol of mechanical testing is then developed. Each stage of the project contributes to compiling a list of materials and techniques, assessing their advantage and limitation in light of both the literature review and the results of our mechanical experiments. The survey part is presented by Anne-Sophie Gagnal, Lise Marandet and Audrey Monet, paper and book conservators at the Montpellier Interuniversity Documentary Cooperation Service in the poster station of the IADA Symposium on Tuesday, 9th of September. After a short literature review about sewing for conservation bindings on parchment manuscripts, this presentation outlines materials, methods, and initial results of mechanical testing. Key areas of study include mechanical behavior of materials. It consists of an evaluation of sewing thread and supports, mechanical behavior of models according to the sewing techniques and sewing supports, stereo correlation imaging, which allows visualization and measurement of the spine deformation during opening. Then come discussion and conclusion. All documentation follows an open science approach, and you can find raw data and report on data warehouse. You can find the link in the description part of this video. Many medieval manuscripts on parchment have lost their binding or have been rebound later, generally in the 19th or 20th centuries, in library bindings, without considering their specific characteristics. The concept of conservation binding was therefore developed to propose an approach of rebinding that would respect the conservation ethics and the mechanical specificity of the text block. However, few studies in book mechanics have been carried out since. Studies conducted by Anders, Ziermay and Wellhauser carried out in 1999 and by Paula Steer published in 2024. However, even today, technical and material choices are frequently dependent on experience, sensitivity, technical skills, and knowledge of a person or an institution. This knowledge is not always published and quantitative data is lacking. The sewing is the most important stage in the making of a conservation binding. When a book is opened, the convex spine gradually takes a concave shape as the materials undergo alternatively compression and tension forces. According to Tom Coyne-Roy, a large concave deformation of the spine in the form of an arc is necessary for parchment text blocks in order to obtain a tension-free opening and a good flatness of the leaves. To obtain this result, Robert Espinosa and Christopher Clarkson recommend sewing on support using a sewing frame, which should form a natural rounding and backing without the use of any adhesives. Sewing before 1500 are a great source of inspiration. However, it's not enough to copy ancient techniques. We must try to understand their specific mechanical features and the need they meet. The main characteristic required for conservation binding to meet durability, mechanical and chemical harmlessness criteria include obtaining a wide and uniform arc on the spine when the binding is open in order to spread tension and compression forces. Selectioning materials and techniques in relation to the text block feature and its mechanical behavior, and obtaining opening in which the leaves are as flat as possible to avoid mechanical stress on the media. According to the literature and conservation ethics, the sewing support and threads must be chemically and mechanically compatible with the original materials. That means for sewing threads, natural, unbleached and undressed fibers to meet the ethics in terms of chemical compatibility and aging. Also a good tension strength, large diameter to limit the risk of tearing in the center fold of the signature during the sewing. A sufficient flexibility and allow swelling control during the sewing. Multiplies thread and low extensibility. For sewing support, a good tensile strength to hold the boards and compressive strength to withstand book openings. A good flexibility-rigidity ratio to support the text blocks during the spine binding. Low extensibility to avoid the risk of over-tensioning sewing support on the sewing frame and creating a concave spine when they are released. Give preference to 3 or 6 double sewing supports to avoid the risk of lateral twisting of the spine and the boards between them, with a diameter adapted to the text block dimensions.
For mechanical testing, the first part is dedicated to the characterization of the mechanical behavior of the sewing materials, threads and sewing supports. This characterization was carried out at the Solid Mechanics Laboratory at the École Polytechnique in Palaiseau by a third-year bachelor student, Charlotte Boleslawski, under the supervision of Dr. Julie Diani, CNRS Research Director in the Mechanics of Materials. This work has been presented in an article available in the last issue of the Journal of the Institute of Conservation. You can find the link in the description part. The second part is dedicated to the mechanical behavior of models by the measurement of curvature of the spine, then by a mechanical fatigue test. This study was conducted by us at the Conservation Studio at Sorbonne Interuniversity Library. The last part is dedicated to stereocorrelation imaging and carried out by the Solid Mechanics Laboratory at the École Polytechnique in Palaiseau. For the mechanical testing on materials, sewing threads and support samples were selected based on the literature and their availability on the market. We selected 8 sewing threads, 6 composed of linen fibers, which has been widely used in bookbinding throughout history, and 2 composed of nettle fibers, which were shown to be promising by the study conducted by Enders, Zermay, and Wellhauser in 1999. A strain-to-failure test was conducted to characterize the mechanical behavior on the sewing thread using monotonic and cyclic uniaxial tension test. You can see the technical specifications of each test. Here, the results. The linen threads without finishing and aging are in pink. The linen thread B with 2 plies has a higher tensile strength than the thread C with 5 plies. Thread B is also more resistant and less extensible, despite coming from the same supplier as thread A and being finer, with the same number of plies, which is counterintuitive. The dressed linen thread D in blue shown the best stress strain response, probably because dressing limits variability in diameter. However, the addition of a finish also raises questions regarding fibers aging, as demonstrated by the results for threads E and F in yellow. Finally, the nettle fiber thread G and H in grid did not behave satisfactorily, probably because only single-ply threads could be found commercially. The results for the sewing thread make it possible to classify them according to extensibility and tensile strength. The results of the cyclic uniaxial tension test showed no breakage after 5,000 cycles. Consequently, the breaks sometimes observed during sewing seems to be caused by abrasion of the thread on the parchment folios and sewing support than by repeated traction. After application of the first load, a significant distortion was revealed. A residual strain of over 37% was calculated for each thread after a 13 Newton load cycle was applied, followed by a zero stress discharge for 250 seconds. A tensile test was also performed to characterize the mechanical behavior of sewing supports. The sewing supports selected for samples are the most commonly observed in medieval manuscripts: split, twisted, and flat thongs made from allen-towed skins of calf and goat and linen cords. As the skin is anisotropic, the thongs were cut in both spine and transverse direction, according to the Hafner standard. Due to its thinness, the goat skin was lined with a second layer, which was adhered using wet starch paste. A monotonic uniaxial tension test was carried out on the sewing supports. You can see the technical specifications of the test. The obtained results indicate that calfskin thongs are made resistant and rigid in the spine direction than in the transverse direction. In contrast, goatskin thongs break equally in both directions. Twisted supports stretch significantly even when the applied stress is low, due to their helical structure. However, their strength before breakage is similar to that of flat split thongs. Linen cord is stiffer and deforms little than allen-towed skin thongs. We now turn to the study of mechanical behavior of the models. To compare the mechanical behavior and durability of various sewing techniques and supports, several tests were conducted by the conservation studio on 2 corpuses of models. The first corpus varies the types of sewing. We made 3 models with single straight sewing, packed strain sewing, and herringbone sewing, all on double linen cord. These types of sewings are commonly observed on medieval parchment manuscripts and are used in conservation bindings on medieval manuscripts. Single straight sewing is commonly used, but leaves empty spaces between the thread on the sewing supports according to the thickness of the signatures. According to literature, it occurs localized stress zones and an uneven distribution of stress on the spine. To counter this phenomenon, the Romanesque bookbinders used packed sewing, adding turns of thread to fill the empty space between the signatures and stiffen the sewing supports. According to the literature, packed sewing creates a mechanical action called spring effect by creating a wider arc and more uniform flexion of the spine, which limits the compression forces on the sewing supports. Herringbone sewing allows the signatures to be linked together at each sewing support, in addition to the changeover station. The text block is compact, fully supported, and can withstand the degradation of sewing supports, like a sort of Coptic sewing on a support. According to the study conducted by Anders, Ziermay, and Wellhauser, herringbone and changeover station stitches cause abrasion on the sewing thread due to overlapping threads. 3 samples of each model are made. To compare the impact of the type of sewing support, the second corpus is composed of 3 models sewn on double linen cord and split flat and twisted Allen-Towitz goatskin thongs, all sewn with a single straight sewing. It's the same materials which were experimented in the first part by the Solid Mechanics Lab at École Polytechnique. As previously, 3 samples of each model were made. About the models making, the selection of materials and techniques and their interaction are designed to simulate the mechanical properties of medieval manuscript on parchment. Each model comprises a text block with 15 signatures of 4 bifolios of paper, which are rigid to a similar degree to parchment. The sewing supports are laced in cardboard boards and pasted with Evacon air on the inner boards. The marking up and dimensions of the text block are based on those of the models made by Christopher Clarkson all along his career. The first step in characterizing the properties of each model tip is to compare the arc formed by the spine when the book is open to 180 degrees at its central bifolio. The arc is measured according to the determination of curve standard to calculate the curvature of the spine. We measure the chord C and the height of the spine through H, as you can see on the diagram. Then we put the data measurements in the formula to calculate the magnitude of curl called K. To evaluate each arc, we establish an ideal K value of 83.3, which corresponds to a perfect semicircular arc. A standardized photography protocol was carried out to compare visuals and quantitative data. Here the results according to sewing types. Pack sewing produces the widest arc, which is closest to the reference value. Single straight sewing produces a tighter arc, and herringbone sewing produces the tightest and highest arc. All quantitative data are correlated with the visuals of the photography protocol below. The results are according to the sewing supports. Twisting thong provides the widest arc, closest to the reference value. The flat split thongs have a slightly narrower arc, but is also quite close to the reference value. Finally, the linen cord produces the narrowest and highest arc. As previously, quantitative data are correlated with the visuals of the photography protocol below. The following test on models involves reproducing the mechanical fatigue as a study conducted by Anders, Ziermay, and Wellhauser in 1999. We use a test bench prototype developed by Astrid Martin during her master degree in book conservation at Lacombe School in Belgium. The test bench performs 72 opening cycles per minute, opening the book in its central bifolio to 180 degrees. Each model is opened for 20 hours. A photography protocol is carried out before each hour of opening and closing, comprising a photograph of the full spine and 5 detailed views of each sewing support and changeover station at the location of the opening. You can see an example after 20 hours. There are several failures on the linen cord. The planned 20 hours of testing could not be carried out on all the models due to a failure on the test bench prototype. The models on tongs could only be tested for 13 hours, which nevertheless produced some results. So, after 13 hours of testing, the models sewn on tongs show no visible damage, unlike the models sewn on linen cord. You can see the results of fatigue tests according to sewing types. The models with packed straight sewing and those with single straight sewing show similar results. After 20 hours of stress, 2 of the 3 models with single straight sewing show all of their sewing supports broken, and 2 of the 3 models with packed straight sewing show 2 broken sewing supports. However, the first alteration appears on average after 10 hours of stress for packed sewing and after 12 hours for the single straight sewing. All the models sewn with herringbone sewing show breaks on all their supports before 20 hours of stress. Most have several breaks on the same support, and first alterations appear on average after 9 hours of stress. Unlike the test conducted by Anders, Zermay and Wellhauser, no sewing threads broke during the fatigue test, so we didn't notice abrasion phenomenon on herringbone and changeover station stitches. Finally, an experimental test by stereocorrelation was conducted by the Solid Mechanics Lab to calculate the deformations and displacements of a surface under mechanical stress. Stereocorrelation technique allows to measure the displacement between 2 images of a surface, using 2 lenses to calculate 3D deformations. The model provided by the Conservation Studio is a paper text block sewn using herringbone sewing onto the linen cord. An adhesive tape with a pattern of dots is applied to the spine. This allows to calculate the displacement and deformation of the spine at the opening. The surface profile was reconstructed using digital image correlation. The book model was positioning upright and opened at 45 degrees and 90 degrees. A compression of around 2.5% to 4% was determined for the 45 degree and 90 degree openings. You can see that the signature folds are closer together near the compression bands.
Discussion on materials testing. First, about sewing thread. The number of plies is not the only factor to consider when choosing a sewing thread. Other factors also have a strong influence on mechanical strain, such as the twist rate, which unfortunately could not be evaluated in this study, and also the regularity of the diameter, which improves the stress-strain response. We saw that dressed thread appeared to be stronger, which is probably due to the fact that the addition of finish limits variation in diameter. However, the addition of dressing to the thread raises questions about fiber hedging. Unfortunately, needle fiber could not be fully tested and merit further experimentation. We have also seen that when a thread is put under tension, it deforms irreversibly. This means that during sewing, the tension exerted on the thread causes it to stretch. Once the tension has been released, some of this extension remains permanent, even when the thread is tensioned for the first time. This is why it's important to use low extensible threads in order to avoid creating fragile areas. Regarding sewing supports, calf skin seems more suitable than goat skin for this purpose, as suggested by Christopher Clarkson in the literature. It's indeed more rigid. Similarly, flat tongues, because they are stiffer, seem more suitable than twisted tongues. The low extensibility of the sewing supports avoid creating a concave spine, when the book is closed. Line and chords are really resistant to traction, which can be an advantage when the binding as heavy boards, for example. The test on models carried out by the conservation studio has allowed to refine the interpretation of the material tests. Pack sewing appeared to be the most suitable for creating a wide spine arc. This confirmed data from the literature, in particular the fact that it stiffened the sewing support. Herringbone sewing, on the other hand, produced a tighter, more angular arc. We can presume that this effect can be modified by the combination of herringbone sewing and Halontung skin tone. Herringbone sewing is still an interesting option, however, if the text block needs to be held more firmly and compactly. A comparison of the result of mechanic fatigue test, the spine curvature measurement, and the photography protocol show a clear correlation between the shape of the spine arc and the mechanical fatigue strain. If the arc is wider and more uniform, the sewing supports are better protected. The opening and closing of the book primarily affect the sewing supports, which are exposed to repeat compression. Finally, the sewing thread is subjected to very little stress, and we did not observe any breakage or abrasion, despite the high number of test cycles, up to 86,400, on all the models. Finally, the measurement made by sterile correlation confirmed the observation report in the literature. The deformation of the spine during opening is also created by displacement of the spine folds relative to each other, as suggested by Paul last year. This experiment is a promising step because it allows quantitative measurement of spine deformations. Its use opens up interesting perspectives, such as the possibility of modeling the forces acting on the spine and of virtually varying the technical scenarios, such as number and diameter of sewing supports or marking up for the sewing, for example. While this research has brought valuable insights, there are still some limitations to keep in mind. In particular, when it comes to study sewing materials, more target experiments are needed. Ideally, using threads that differ by just one variable at a time, such as fiber type, number of ply, density, finishing treatment, or aging. One challenge we faced was reeling commercially available threads, where the exact composition and manufacturing process aren't fully disclosed. This makes it harder to interpret the result with precision. That's why developing custom-made samples tailored to specific experimental needs is a promising direction. It will allow us to better understand the impact of each characteristic on the performance of threads and cord using in sewing. The main limitation of the study conducted by the Bees Conservation Studio is the insufficient number of models using during the mechanical fatigue test. The time required for each model to pass through between 13 and 20 hours, as well as the limited endurance of the test bench, force us to reduce the number of models per type to 3. This doesn't allow for a good repeatability of the results and therefore requires them to be approached with caution. The third limitation is that the production of the samples require numerous handcraft steps. Some variations are possible between the model on aspects that is difficult to quantify, such as the tension exerted on the thread during sewing. The lack of information and the variability in the quality of materials used in conservation is also a point to consider. For example, it's impossible to obtain two identical skins. The mechanical behavior therefore depends both on the skin obtained and on the sampling area. Similarly, it is rare to know the twist rate of a thread or a cord. The use of custom-made cord samples could provide greater repeatability of the results and improve their relevance. Finally, the study does not consider the aging of the materials. In conclusion, this study explores the impact of sewing structure and sewing support on the mechanical behavior and strength of the bindings. The result obtained highlights significant trends, although some methodological limitations call for caution interpretation. So this study represents an initial exploration. It highlights promising avenue, which also underline the need of further experimentation to refine our understanding of the mechanical involved to the relevance of material choices in the context of crafting conservation bindings for parchment text blocks. We hope that these research avenues will be explored by colleagues in future. With this in mind, all documentation produced during this research follows an open science approach in order to enrich the international dialogue on conservation practice. Future researches could address sewing, spine bindings, lacing, or boat shaping. We are grateful to Dr. Julie Diani and Charlotte Boleslaski, also to Sylvie Strive, and to our colleagues of Montpellier Conservation Studio, Anne-Sophie Gagnal, Lise Marondet, and Audrey Monet. Also to Bathilde Grenier, Daria Gorbachevska, and Nadine Dumas. Thank you for your attention.